Hi there. Today we're here to talk about logistic regression, and this will be an introductory video on the topic. This video series was composed by Mitch Borgert, Martin Eong, Lindsay McPhillips, John Morgan, and Kelso Kwan. Within this series, you will see a video on each of the following topics: the introduction to logistic regression, which is the current video that you're watching, applying logistic regression to create a simple and well-fitted model, and then applying logistic regression to a more complex model with multiple X independent variables, and the diagnostics for the logistical regression model. And please note that R&R Studio was used to do all diagnostics, model fitting, as well as conclusions. Logistic regression is a technique used to model data when the response or subject that you're interested in is binary, meaning that the yi will be coded as a 1, 0, or it could when the true meaning could be a true, false, raining, not raining, basically anything in which you could code it in a 1, 0 situation. And logistic regression also uses the same ideas as linear regression, where there's one response variable, which is the y, and one or more independent variables, being the x's, and beta coefficients to go along in the formula. When modeling an event with probability 0 or 1, the graph of the regression equation is generally considered an S-curve. And this is because as you go from 0 to 1 over the course of the model, you will see that basically the probability resembles that of an S, where it's starting to 0 and then over the course of the time it goes over to 1. Because this shape of the logistic regression curve is an S, is why this is considered to be a nonlinear regression model. The model assumptions for logistic regression are as follows. The dependent variable needs to be categorical. It's basically something that can be split into a binary 1 or 0. All observations must also be independent, and the independent variables must not be linear combinations of one another, as this will lead to correlation issues among the independent variables. And a larger sample size than linear regression is also required. So since yi is a binary response with form 1 and 0, yi can be considered to be a Bernoulli random variable. So when yi equals 1, the conditional probability is easily modeled as the probability density function of the logistic distribution. In the case of simple logistic regression, the conditional probability statement will take the same form as the logistic PDF as seen in this first equation, except you can replace the exponent from the PDF with beta naught and beta 1x for simple logistic regression. Now in order to make this a little easier to digest, we'll bring up the discussion of the odds of the event, which are defined as the probability of the event happening divided by the 1 minus that probability. When you set p in that odds equation to the conditional probability as defined above, you transform the conditional probability into the odds function, and it becomes much easier to deal with in that it's simply the exponential term to the simple logistics equation in that exponent. So given now that conditional odds are equal to e to the basic linear regression model as the exponent, in order to make this easier to deal with, we're going to take the log of those conditional odds, which give you just that basic linear regression model of beta naught plus beta 1 x1. And it's worth noting here that 1 unit on the log odds scale is referred to as a logit. So in looking at the difference between yi at points xi and xi plus 1, we're able to find the true meaning of beta 1. So using log rules, we're able to make that difference a fraction within the logarithm. And from there, it can be shown in this slide that the difference between log odds at xi plus 1 minus the log odds at xi equals x are simply equal to beta 1, meaning as yi goes from x to x plus 1, beta 1 is the multiplicative increase in log odds from x to x plus 1. So if you are modeling the hours of studying for the comprehensive exam onto whether or not the student passes the test, beta 1 would be the increase in log odds of passing the test when the student has an additional hour to study for the exam. So using the logistics regression curve, you could also see when the additional studying would result in a highly diminished increasing odds, aka when it's time to stop studying. And please note that this definition for beta 1 works for beta I in the sense that if you were doing a multiple model, then your definition for the beta would be the same in that it's the multiplicative increase as x progresses to x plus 1. So now for beta naught, this is the log odds of what's being categorized by y given that x equals 0. So in the previous example, beta naught would be a student's log odds of passing the exam without studying for it at all, which in that case, as you can imagine, would probably be very close to 0. So odds ratio is a useful statistic used to identify relationships between the dependent and independent variables. In a simple logistic model with only one predictor variable, the odds ratio is defined as the odds when x equals 1 divided by the odds when x equals 0. So therefore, an odds ratio equal to 1 suggests there is no relationship between the predictor variable x and the dependent variable y, because those odds are exactly the same. But an odds ratio greater than 1 suggests a positive relationship between the x and y, meaning as the greater that x gets, the higher chance that y equals 1. And likewise, an odd ratio less than 1 suggests a negative relationship between x and y. And because these are two factors divided by one another, odds ratio is always greater than 0. If you have a simple logistic model where x is coded categorically with a 1 if a student received an A in all SDSU statistics core classes, being 610 and 670 A and B, and a 0 if not all A's in those classes, and the Y as the outcome of the student's comprehensive exam, one would expect an odds ratio greater than 1 because there should be a positive relationship between receiving A's in the core classes and passing the exam. Conversely, if X was coded as the amount of lectures missed by a student for their core classes, then one would expect an odds ratio less than 1, signifying a negative relationship between missing lectures and passing the comprehensive exam. Some of the main differences between logistic and linear regression are that graphing logistic regression yields an S-curve instead of a line for linear regression, and that logistic regression is concerned with the probability of an outcome, while linear regression is concerned with the value of that outcome due to its continuous dependent variables. Logistic regression requires a categorical dependent variable, while linear regression requires a continuous dependent variable. The conditional expectation of the dependent variables in logistic regression is distributed as Bernoulli random variables, whereas linear regression continuous variables are distributed as normal random variables.